Hi everyone, Miss Caulfield here. In today's video, we are going to be looking at how to interpret and read element symbols on a periodic table and how those element symbols are altered when we are talking about isotopes and ions. So starting us out, we have a pretty typical element symbol, or a very typical box you would see on a periodic table. There are a couple of important pieces to an element symbol. So we have the element name, which is going to be the full name of the element that we're talking about. The element symbol, which is going to be used anytime you're trying to abbreviate the element that you're talking about. For example, when you're writing a chemical formula or you're using those chemical formulas when you're writing a chemical reaction, that element symbol is what we use to understand which elements are involved in the formula or the reaction. We also see electronegativity in the bottom right-hand corner. We're going to pass on that for right now, but we will be talking about it in the coming weeks. Looking on the right-hand side, we see that we have something called the atomic number and the average mass. So the atomic number is the same thing as the number of protons in an atom. The number of protons, or the atomic number, is the identifier for different elements. If you're talking about an element, it will always have the same number of protons or the same atomic number. As soon as you change the number of protons, you're no longer discussing the same element. Changing the number of protons changes the element. In the bottom, we see this thing called average mass. Average mass is a weighted average of the different isotopes of an element. We will be talking about that in our average atomic mass video. What we want to look at here is when we round this average mass, so when rounded to the nearest whole number. So when we round that average mass to the nearest whole number, you get the element's mass number. And an element's mass number is equal to the number of protons plus the number of neutrons. So if you remember from our video on subatomic particles, the proton and the neutron both have a relative mass of 1 AMU. So those two subatomic particles will be contributing to the mass of the atom, whereas the electron has a relative mass of about 0.0005 AMUs, so it's much, much smaller and won't be contributing to that mass, which is why it is not included in the mass number calculation. So if we were to look at this example here, the mass number for mercury, when we round 200.59 to the nearest whole number, is going to be 201. So we just round it to the nearest whole number to figure out that mass number. So what we saw previously is a very typical element symbol, but different sources use different element symbols, and each one has slightly different information on it. So it's important for us to be able to pull out the relevant information on any element symbol that we see. So looking at this example here, the question is, how many protons are in lead? Well, to answer this question, we would need to identify which part of this element symbol is the atomic number. And the atomic number is going to be this 82. And so since this atomic number is 82, we would say that there are 82 protons in lead because the atomic number and the number of protons are the same. Our next question is, how many neutrons are in an atom of lead? So in order to answer this question, we need to first take this atomic mass. Remember, the atomic mass is going to be the one with the decimal, and we need to round it to the nearest whole number. So the mass number for lead is going to be 207, because when we round 207.2 to the nearest whole number, we get 207. We're going to do that equation of mass number equals number of protons plus number of neutrons. We're going to rearrange it to solve for the number of neutrons, which is what our question is asking us to do. So we'll do 207 minus 82, which is what we identified in the last problem as the number of protons, and we get 125 neutrons as our answer. So now that we've had a chance to learn how to read element symbols on the periodic table, let's take a look at what happens to the element symbol when we're dealing with isotopes and ions. So the first one that we're looking at here are isotopes. If you take a look, we can see that we've got three different element symbols. We've got 1 over 1H, 2 over 1H, and 3 over 1H. So we can use this key down here at the bottom to see which ones are the atomic numbers and which ones are the mass number. So the bottom number in each of these, this 1, represents the atomic number, whereas the 3 at the top represents the mass number. If you notice, the atomic number is staying the same for each of the isotopes, and that is because we cannot change the number of protons or the atomic number and still be talking about the same element. If we do take a look at it though, it looks like our mass number, the 1, 2, and 3, are changing. That color is not very great, so I'm going to go ahead and erase those and highlight them in a different color so that they are more visible. So we've got the 1, 2, and the 3 here, which are showing that the mass number is increasing, and the only thing that is increasing based off of our key is this idea of the neutrons. So when we take a look at those 3 hydrogen atoms, we see that this first box here has no neutrons, the second box has 1 neutron, and the third box has 2 neutrons. We know that that mass number is equal to protons plus neutrons, and so that makes sense for why we see the mass numbers increasing from 1 to 2 to 3. On the bottom of the screen, we see a second example looking at 3 isotopes of carbon. Again, we see that that atomic number of 6 protons each is going to stay the same, but as we increase in the number of neutrons in the isotope, then that mass number, that top number, is increasing respectively to how many neutrons are added to the atom. So now that we've had a chance to look at how changing the number of neutrons affects the element symbol, let's take a look at how changing the number of electrons also affects the element symbol. So we're going to start by taking a look at this element symbol for fluorine here. Here we see that the mass number is 19. The atomic number is 9. So our mass number is 19. Our atomic number is 9, meaning that we have 9 protons, which is what it shows in the picture. If we go ahead and count the number of black circles in this atom of fluorine, we're going to see that we have 9 protons and 9 electrons. Atoms have a neutral charge. A neutral charge is having an overall charge of 0. So if we know that we have 9 protons, then we know we're going to need 9 electrons to cancel out those 9 positive charges. When we take a look at the ion picture on the right, we see that we still have 9 protons because we're still talking about the element fluorine. We see that in the element symbol. But now when we count the black circles, we see that we have 10 electrons. So there is 1 negative charge that is not being canceled out by the protons, which is causing this overall charge of -1 for the fluorine ion. Now let's take a look at the bottom image. So in this bottom image, we see that we've got an atom of magnesium, and that atom of magnesium has 12 protons, because its atomic number is 12, and there are 12 electrons pictured. There are 12 black circles here. So that atom is neutral. Anytime we're talking about an atom, we're talking about something that is neutral, so the number of protons has to be equal to the number of electrons. But when we take a look at the ion, we see that we still have 12 protons, but now instead of 12 electrons, we only have 10 electrons. So there are 2 more positive charges than negative charges, which is leading to this overall charge on the ion of positive 2. So here's a good practice question. An ion of chlorine has a charge of negative 1. How many electrons does an ion of chlorine have? Well, if we take a look at the element symbol here, remember the element symbols are for atoms. So this is going to be our atomic number is 17. So in an atom of chlorine, we're going to have 17 protons, which means we need to have 17 electrons to cancel out those 17 positive charges. In an ion of chlorine, we're still going to have 17 protons because the number of protons always has to remain the same. But now we have a charge of negative 1, which is given to us in the problem. So we have to think about how many electrons would we need for there to be an overall charge of negative 1. So that means we need one more electron than we have protons. So the total number of electrons we would need would be 18 electrons.